Okay, so here's our second video on Dalton's Law, and this is Dalton's Law practice problems. And so hopefully you've already watched the video on Dalton's Law of partial pressure, which we did notes on page maternity leave 109. And so we talked about how Dalton's Law had three kind of parts to it. That Dalton's Law is always about a mixture of gases, and we know the total pressure is equal to the parts added up. We know that the gas pressure of each gas in the mixture is relative to its percent volume. And finally, we learned about this thing about collecting gas over water. And so when we collect a gas over water, we have to take into account the vapor pressure of the water pushing up. And one of the other things we learned is that the partial pressure over the total pressure is relative to the partial volume over the total volume, and we use this equation to kind of work through some of our problems. Okay, so we learned that when we're collected over water, and we have like a beaker of gas collected over water, that the water vapor is adding to the total pressure, and that the amount of push that the water vapor gives is relative to its temperature. And so we learned to look in Appendix A of the old textbook. So if we go to the old textbook and we look at page 859, we'll see the water vapor pressure table, and it has the temperatures and the pressures in both mmHg and kPa. Okay, so you have a worksheet that you're doing on Dalton's Law, and that worksheet is pretty straightforward. It was on page maternity leave 108, and there's an answer key provided for you. I think you're going to be fine on that. I wanted to go over some of the problems from the textbook, and so these are the problems that you're going to physically work out on page 108, and they're from the textbook. The old textbook is pages 896 through 897, Appendix D, and so if we go here to pages 896, we're looking at problem number 251 today, and then on page 897, I'm looking at problem 266. And so I've written them out to kind of speed up the process for us, so I don't have to keep going back and forth. Okay, so it says a chemist for problem, I'm sorry, actually I lied, it's page problem 250. A chemist collects a sample of H2S over water at a temperature of 27 degrees Celsius. The total pressure of that gas that's been displaced, 15 milliliters, is 207.33 kPa. What's the pressure of the H2O gas? Okay, I always draw a picture. So I know that I have over water, and I know that that water temperature is 27 degrees Celsius. That's going to be important. And then I have my gas container above that. It tells me that the total pressure of the system is 207.33 kPa. That's my total pressure. And I want to know, well, what's the pressure of the gas inside? Okay, so I know that the water vapor pressure plus the gas pressure is going to equal 207.33 kPa. I need to know what the water vapor pressure is at 27 degrees Celsius. So I'm going to flip into my textbook, table A, water vapor. I'm going to go to 27 degrees Celsius, and I'm in kPa, so I'm going to use 3.57. So I know that let me just double check and make sure, because I wrote down something else earlier. For problem 250, 27 degrees Celsius. Yep, okay. So 27 degrees Celsius is 3.57. So I'm going to take 207.33 kPa, and I said that it was 3.57. So it's 3.57 kPa for water vapor. So 207.33 minus 3.57 kPa is going to give me the pressure of the gas. And so I take the total minus the water, and it's going to give me the gas. The total was 207.33 kPa. The water vapor pressure was 3.57 kPa at that pressure of 27 degrees Celsius. And so 207.33 minus 3.57 is going to give me a pressure of the gas of 203.76 kPa. Luckily, everything was in the same unit, so I didn't have to subtract anything. And so that's my first problem. I'm going to go back and fix my answer key that I gave you guys, because I did not use the right values. 3.57 gives us 203.76 kPa. Okay, I fixed it. All right, so now let's look at the third problem that you have. which is going to involve a couple of different pieces. Again, we're going to draw a picture. We're going to read through what they talked about. I know that it says it's collected over water, so I'm going to go ahead and draw my picture. I've got my water. I know the temperature of the water is 17 degrees Celsius. And so I'm going to be collecting a gas over water. Okay, the total volume, so I'm going to write that down because that might matter. Total volume is 0.461 liters, and the total pressure is 0.989 ATMs. Okay, so they want to know what is the pressure due to the gas. What is the pressure due to the gas? Well, here's my gas inside here. So the first thing I need to know is I need to know, well, what's the pressure of the water at 17 degrees Celsius? So I go back to that table in the textbook and I look it up, and the pressure of the gas at, or the pressure of the water vapor at 17 degrees Celsius is 1.94 kPa. This pen has seen better days. So let's switch that over. I'm going to switch to orange. 1.94 kPa is the pressure of the water vapor. But the problem is that everything else is in ATMs. So I'm just going to go ahead and convert this, knowing that my conversion of 101.3 kPa equals 1 ATM, just that I'm talking in the same units. And so if I take 1.94 divided by 101.3 kPa, so 1.94 divided by 101.3 kPa gives me 0.19 ATMs, and that's the water vapor pressure. Okay, so if I know that the total pressure is 0.89 ATMs, and then the water vapor pressure is 0.19, I can say, well, the total pressure is 0.989 minus the vapor pressure, 0.019, is going to give me a partial pressure. So I'm going to take 0.989 minus 0.019, and I get an answer of 0.97 ATMs. Okay, so this is my gas pressure. So what's the pressure of the dry gas collected? 0.97 ATMs. That was pretty easy. If they had asked me for the volume, what I could say is I could say, well, I know that the partial pressure, so the partial volume over the total volume is equal to the partial pressure over the total pressure. And then I could say, okay, well, if they're asking me for the partial volume, I know from the problem that my total volume was 0.461 liters, and I know that my partial pressure is now 0.97 ATMs. My total pressure was 0.98 ATMs, and so I could just cross multiply and divide. So 0.461 times 0.97 divided by 0.98 would give me a partial volume. So the volume of the gas would be 0.456 liters. They didn't ask me to do that, but I just wanted to show you that you can take two problems and kind of combine both of those things. In this case, they just asked us what is the pressure of the dry gases. So that's what I gave you. Okay, so hopefully this helps you solve Dalton's law when we're collecting a gas over water.